Sometimes derivatives throw us kind of sideways when they ask us to interpret in the context of a word problem what it means. So let's look at a problem here. This is one of the problems that Stewart, out of one of his books, Concepts and Contexts for Calculus, put together. How do we interpret the derivative? Especially, what are the units that are being dealt with? So one of the problems in Stewart's book says, let Q of P be the quantity of coffee sold at the price P dollars per pound. And they ask us, would Q prime, would the derivative of the Q function at 8 be positive or negative? And would the derivative function at 30, Q prime of 30, be bigger or smaller than Q prime at 8? So the first thing to do with a problem like this and understanding it, you need to go ahead and kind of figure out graphically what is on your x-axis or horizontal axis and what is on your y-axis. The way they set this up is P is going into Q. That means that P represents the input down here. So P would represent our dollars per pound that we sell coffee for, which means the vertical axis is Q, capital Q, and this is going to tell us the quantity of coffee that we sell. This will be presumably in the pounds of coffee that we're selling at a certain price. Now, if you're really bad at numbers, just try to plug some numbers in to see what's going on. So the worst case scenario here is that coffee might be $0 per pound. Then it could be, I don't know, $5 per pound. You just got to put in some numbers that seem feasible and keep on working. So let's kind of make a graph of what we would expect to have happen. This in quantity, we don't really have to have a certain quantity here. We just need to feel out the graph. If we're selling coffee for nothing, it's totally free. Let's assume the coffee is good. How much coffee will we sell? Well, we would sell an infinite amount of coffee. Because, hey, who doesn't want free coffee that's good coffee? All right, so we don't have enough of that to sell. It's way off the chart, way over the top. So now we ask, all right, what about as we start to charge some? Well, as we start to charge some, the amount we sell starts to go down. The more we charge, as we keep on going this way, $5 a pound, $10 a pound, we're going to sell less coffee. Okay, that makes sense. So the shape of the graph is going to do this as we keep on going out. How far is this going to go? I don't know, but eventually coffee is going to get really expensive. How expensive? It gets as expensive as you want it. The most expensive coffee in the world right now ranges anywhere between $300 a pound and $1,000 a pound. You should go look it up. Most expensive coffee in the world. It is basically created by felines that eat coffee beans whole. Their tummy does not cause it to go away, and then they poop out magic coffee beans that are roasted, ground up, brewed, and then consumed by humans all over the world for exorbitant prices. So if you look it up, this could feasibly keep on going out in the price very far. So way, way out here. How much coffee is going to get sold at that price? Most of us don't pay more than about $10 to $20 a pound for coffee. So as that $300 mark or $1,000 mark keeps on going, we're not going to sell that much coffee. We're going to sell very little. So this is going to keep on going down. The quantity gets lower because coffee is getting too expensive. Will it ever eventually cross over this horizontal axis? That's a theoretical question. Is there a price at which nobody would buy coffee? Maybe, maybe not. Usually, there's always one crazy person in the world that has a lot of money that doesn't know what to do with it, and they love to brag about how much they spent on stuff. So my theory is it would take an outrageous amount for this to ever even hit the x-axis where nothing is sold. Why? Because you can sell $1 million a pound coffee, and there's probably somebody that'll buy it. So this is probably asymptotic to the horizontal price of coffee per pound. Now we've got to go back. What does this mean about the derivative? Well, the derivative is the slope of a tangent line at a fixed point. So right here, we're saying fix the price of coffee to $8 a pound. Okay, there's $8 a pound. Go up to the graph, somewhere about right here. We're assuming this is a continuous graph. And now we ask the question, Q prime of 8 would be what? Well, go to where P is 8, go to the height of the graph, that's Q of 8, and make a tangent line. All right, well, the tangent line, if we tried to make one, would probably do something like this. Tangent, of course, meaning just barely touching. Tangents means to touch. It would do this. The question is, what's the slope of that line? Well, the slope of the line, it's going down to the right, so the slope is negative. So what do we know? We know that Q prime at 8, when the price is fixed at 8, is negative. Why? Well, simple. As the price increases, the quantity is decreasing. So the slope of our line, or the tangent, when price is 8, is going down. Price of coffee is going, or the quantity sold is going down as the price increases. Now the question becomes more interesting in part B. Would Q prime at 30 be bigger or smaller than Q prime at 8? Well, just go make a tick mark, all right? So where's the tick mark? We need to go over to 30. That's where we're worried about now. 30 would be way out here. We go up to the height of our graph. We make a tangent line. The tangent line would be something like this. Doesn't have to be perfect. Just trying to give us an idea. It keeps going in both directions. Is that tangent line indicating that Q prime of 30 is bigger or smaller than Q prime of 8? It's a question about slope. So the question is, does the slope of the line we just made that's orange, does the slope value look like it would be bigger in value or smaller in value than the slope of the green line that we made? Well, if we think about this, this slope of the green line was negative. The slope of the orange line is also negative, but it's starting to flatten out, which means it's getting really close to a flat line which has slope 0. So even though the orange line is still negative, it's less negative and closer to 0 than the slope of the green line. And because of that, we can say that Q prime of 30 is bigger. Why? Some of us just are mathematically challenged. Think of it this way. If you're talking about the slopes, you could have a positive slope, you could have a negative slope. We just said Q prime of 8 is pretty negative. That would put it graphically about right here. There's Q prime of 8. Where is Q prime of 30? Well, we said Q prime of 30 is negative, but it's not quite as negative. So Q prime at 30 is still negative, but it's closer to 0. Which one of these is bigger? Which one is smaller? We know how this game works. Anything that goes to the right is bigger. So what do we end up concluding? We end up concluding that Q prime of 30 is bigger than Q prime at 8. Hope this helps, gives you a little bit of an idea on how this works. One extra comment to make, sometimes they like to talk about units. The units involved with this, if we throw in an extra question, how about part C? Units that we measure, they are simply rise over run. The rise here is measured in the rise or fall of the vertical axis divided by the run of the horizontal. So the units, just like the slopes that you've done, are in the rise over the run. And that's going to make this a very weird problem because the rise or fall was measured in pounds of coffee that get sold, and we're dividing that by the run. The run is measured in the horizontals dollars per pound. It is the price of coffee per pound. So what would this tell us? If we tried to simplify this, which would probably be a bad idea, you would end up getting pounds sold over 1 times the bottom fraction flipped upside down Pounds times pounds would give you pounds squared over dollars. So in the end, this is probably not a very good example for this. It would be pounds squared per dollar. We never like to deal with these units because they are super awkward in problems like this. What would be an easier case? An easier one is if the vertical indicated miles of travel and the bottom indicated the time it took you to get there. The derivative would represent the vertical miles divided by the hours it took to get you there, which would be miles per hour. So if you've got weird units on your graph, you probably have weird units for the derivative. If you've got fairly simple units on your graph, the derivative will also have simple units as well. Hope you found this helpful. Keep a lookout for more videos in the future here at the Math Informant. You guys have a great weekend and a great day. Take care. Bye-bye.